doesn't. Of the expectation over P of X of F of X minus the same with Q of X of F of X.
Shake weapon.
No. Well, it's over. It's on me.
Thank you, drinking.
Right. Okay. And then you have this is some kind of loss, right? Some kind of norm, actually. Okay. So now, depending on the space that you have here, that F lives in, this error has a different shape. And what you do is basically to sample from the x's, from the learned distribution, and to plug in some of your data, and then you compute the distance between these two functions. So say this is Hilbert space, then this is just a kernel function. So you just try to compute the difference between different data points in your distributions, and then you try to get that as close as possible. Yes. Okay, cool. So this is a generative adversarial network, where we've said, push it through, get some image out. This is our generator. As you can see, it's G of Z. Then we have a discriminator, which is D. D says either this is close to what my data looks like, or this is far apart. But it actually wants it to be far apart. So the discriminator learns to say there is a difference between these distributions. The generator learns to say learns to produce something such that it confuses the discriminator, right? That's why we minimize and maximize. So one of them tries to minimize the difference between the two distributions. The other one tries to maximize it, and then we adjust the parameters of these two iteratively. Right. Yes, so once we have learned these nice neural networks, we can do fantastic things with them. So as I said before, faces are easy, and that's what I think why everyone's using them. Because it's very structured, you don't have to do a lot. What they do here is to take one of the images, that's the source image there, and they try to get a mixture between that one and the destination image. So if you take the kid image, then you can see what all of these people would have looked like kids. This is pretty cool. So I call it neural network magic. All right, cool. There are problems. Lots of problems, as usual. One of them is that, for example, when the discriminator says something is close, it doesn't necessarily have to be close, right? It can look like creepy faces. So one thing that we don't know how to do is the variation, because we humans, we are super good at seeing structure and data. So you see an image and you think, yeah, that could be a car, but actually it's just a red blob on a green background. And we don't have any method to evaluate these things because we don't have access to the real likelihood of the data. So we can only think it looks good, which is not so cool. Then we have one problem that is discrete latent variables, which I think has been more or less solved. So there the problem is that if one is discrete, then you can't push your gradient through it because it will go to infinity. So you basically need to make your discrete latent variables into continuous latent variables, and then it works. Right, and then there's some more problems that I know exist. I'm happy to talk about. I'm over time, so I will just thank you. And this is the link to the real slides. Also, they do have some references in case you're interested.
Did you just use straight that, right?
Well, I just copied the slides. No, so right, this is It's 1.5 talk at the Conference of Uncertainty in AI from 2017. It's online. I haven't looked at it, but if you want to, you can see whether they do a better job. Yeah, questions? Yes?
Yeah, regarding this, I guess first of all it should be minimization of it. Or what are you,
right.
Is this what you wrote in the
yeah, you're trying to minimize that, but the function, so, yeah, sure.
Okay, but I mean, nevertheless, I mean, why don't you care about choosing Q? Or you said you don't care about what you sample.
Right, so you don't care about the form of this. So what you do in variational autoencoders, right, is that you say that the the probability of my image xi given z is product over each of my pixels in this image given z, something like that, right? So you basically say each of the pixels is independent of the next pixel, which is crazy.
So you learn the variational parameters basically.
No,
what is this
no. So this is the formulation of the likelihood of the data.
Okay, but when you go to Q, you ask the mean Q,
yes,
then
yes,
then
yes,
you learn
yes.
the parameters of the
right,
Q.
exactly.
Is that what
yes.
this F represents?
And this one, no.
No, okay, what is F then?
F is just a function that measures the difference between the two distributions.
Okay.
Right, so in the gun case, this would be a form of the discriminator, basically.
So you learn both the variational parameters and this F?
This is not variational inference at all.
Okay, it's not, okay.
No.
Okay.
This is different.
Okay.
Right? Because here, in this case here, we are not interested in the form of Z at all, just interested in this generation.
Okay.
Yes?
In the variational autoencoder, sure, I agree that you sample from the image independently,
Right.
but the correlation is described by the latent variable.
Sure.
Some
But
of it.
so, luckily I know a lot about this because I read up a lot about it. So the problem is, say you train, there's two different data sets. So you have MNIST, and then you have fashion MNIST, where you have like trousers and, I don't know, shoes, also in the same format. But the local statistics of the fashion MNIST cover the local statistics of the normal MNIST. So if you push, if you train on fashion MNIST, right, you train on, I don't know, say this image of trousers, right? And you push that through, you would get out trousers. Then now you push in the number, I don't know, 7 maybe, like this. Okay. You push in this number, this one will be mapped into your latent space close to where all the trousers live. And the model will generate a model, image that looks like the trousers. Now you compute the difference between these two. In the pixel space, if you just look at that, it basically looks like the difference between like this one was filled, that wasn't filled, this one was filled, this wasn't filled, right? And then you have something like this. Well, now the difference between these is actually not that big because in the local statistics it looks the same. So you can't tell, does this image actually come from the data distribution or not? Because this likelihood didn't capture the semantics, it just captured the pixels. And that's the problem.
I agree, but I mean, some of the point of why variational autoencoders work at all is because some of the correlation is captured in the latent variable.
Right, sure. No. I mean, I don't say it's bad.
GANs work better because they capture it better.
They produce sharper images.
Yeah, but they have the same latent sort of variable in that you generate data in the same sense. You can use a hybrid GAN variational autoencoder. It's not
right. Sure.
So it's, yeah.
Yes. What's your point?
I'm just saying that it's not complete. Like the pixels aren't completely independent in variational autoencoder. That was just I wanted to clarify.
Right. No. But we treat them as independent when we score them, and that's a problem.
Sure. And you give them you have encoded like what you're trying to decode.
Yes, supposedly. But you're not going to decode what you intend to.
Any more questions?
Yeah.
So, from the general perspective, when you say that this is a proposal to learn models in general, like this particular implementation means that you learn probability distributions, and that makes a lot of sense for things like if I want to learn that illumination works in certain way for natural images, it sort of comes so that it will be in the statistical distribution. But when another use of model is things like Newton laws or electrodynamics and stuff like that, and I find it hard to wrap my head around to think that those things are statistical distributions that will be learned from the data.
Right.
Is that what this approach is saying? That is everything is probability distributions down to...
No, I would say if you have this knowledge, then you put it into your prior, right? You say this data structured, I know that the latent variables should approximately have this form, and then it's much easier to learn.
Well, okay, fair enough. Be integrated from that.
Yeah.
Thank you.
Cool.
Yeah. Thank you very much.
Thank you.
Thank you. If there's books on the topic of AI, of course.
Awesome. And I know that would have come sooner.
But now, so now there's two options here. We can either stay here and like mingle a bit more for